In this video, we're going to take a look at integration by substitution, and we're going to start with indefinite integrals. Before we learn U-substitution, let's review the chain rule. So remember that when we integrate, it's the inverse of finding the derivative. So any rules that we have when we're differentiating a function have to be taken into account when we apply this in reverse to antiderivatives. So let's recall what the chain rule tells us. When we have a function that is a composite function, so I have a function of a function. When I found the derivative, I took the derivative of the original function and then the derivative of the interior function or the baby function. So let's just remember using this example. This is a function of 2x plus 1 and a function of some value to the third power. It's two functions. When I found the derivative, I used the chain rule and of course the power rule. So this is 3 to the 2x plus 1 to the second power, but then chain rule says now also take it times 2. So this is my derivative. Now yes, I could reduce that, but I'm going to leave it just like that. So now we're going to go in reverse and we're going to think about that chain rule in reverse. So you might see this called pattern recognition, or you might see it called U-substitution. Either way, it's really the same idea. We have to account for the derivative of the interior function. So we're thinking about the chain rule in reverse. So here, if I had, and yes, normally I wouldn't write this all wonky like this with the 2x dx and everything. But I just want to sort of prove a point to us here. So if I'm looking at this integral, it looks like this is a function that is being squared. So that is our composite function. And whenever you have that composite function, that's where you're going to say that u is the 2x plus 1. And then du, which is the same as u prime, is the derivative of that. So that's 2dx. So what I want to do is I want to say, can I rewrite this integral with U-substitution? U-substitution. So the 3 doesn't get replaced by anything, but 2x plus 1 is u. So this is now actually u squared. And then 2dx gets replaced with du. So I'm integrating 3u squared du, so integrating with respect to u. Well, that's going to give me 3 times u cubed over 3, which really just gives me u cubed, and with respect to u. So my answer is just u cubed, and now I'm going to sub the u back in. So u was 2x plus 1 cubed. Now think about where we started. That is exactly where we started. So using U-substitution and keeping in mind the chain rule, we were able to integrate and get back to where we started. So that is U-substitution and or pattern recognition. So if you have the function and you include the derivative of some interior function, then we can integrate back to the original function. As with anything, the more you practice, the more it makes sense, the better you get at it. So I have 4 straightforward practice that are going to fit the pattern exactly. Now for each of these, the biggest challenge is make sure you choose the right u. Now how do I know what to choose for u? Typically it's going to be whatever function has the greatest exponent for x. So for instance here, this is x squared plus 1 and this is 2x to the first. So I'm going to use u as x squared plus 1. Now if you're ever confused about it, u is typically something that is a function within another function. It's a composite function. So this is some function of x squared plus 1 all taken to the 4th power. So that's a composite function. So u is going to be that part in the middle, x squared plus 1, which means du, which is the same as u prime, is going to be 2x dx. Now, the dx is important because what we're going to be doing is we're going to be replacing what we have here and accounting for all of it using u and du. So let's see how we could rewrite this. if I now have the integral of u to the fourth, because u is x squared plus 1, and then I also have 2x and dx. Well, notice that's just du. So I can rewrite that original function, and notice I've accounted for all of the parts, as the integral of u to the fourth du. Now, when I integrate, I'm going to get u to the fifth over 5 plus c. And then I'm just going to replace u with x squared plus 1. So this is the quantity of x squared plus 1 to the fifth divided by 5 plus c. That doesn't look like a 5. All right, let's take a look at the next one. Again, these are all straightforward, so we're not going to have to make the pattern fit. It's already going to fit. This is going to be u. U is inside. That's the x squared plus 1, because that is also a function that is being taken the square root of. So it's a composite function. And then du is the derivative of that, which is 3x squared dx. And if you'll notice, 3x squared dx, and this is going to be u to the 1/2. So I'm going to rewrite this as u to the 1/2 du. Can I do that? Yes, because 3x squared dx is being accounted for by du, and this is u, and then it's the square root of that. So now I'm going to integrate that. This is u to the 3/2 divided by 3/2 plus c. And of course, if you want to go straight to 2/3 u to the 3/2, that's just fine too. And then I'm going to replace u with x cubed plus 1, and then that's to the 3/2 divided by 3 plus c. Let's take a look at the next one. Again, how do I know what to use for u? Well, this is a function inside another function. So I'm taking something and then squaring it. So the function itself is the x squared plus 1, and then the derivative of that is 2x dx. And again, notice 2x dx accounts for everything on the outside. So when I'm rewriting this, I really just have u squared du. So now I'm integrating that, so I'm going to get u cubed over 3 plus c, and then I replace u with x squared plus 1 divided by 3, oh, I think I missed a cubed, and then plus c. So that's my final solution. The last one is, I'm trying to find a different color, but we're striking out here. The last one, a lot of students really struggle with the trig functions because they try to determine, should the trig function be u or should something else be u? So here's an easy way to look at it. If I'm looking at the trig function of cosine of 5x being u, then the derivative of cosine of 5x would be negative 5 sine of 5x. And notice there's no sine in this function. So don't take u and have it be the function of cosine. Instead, let's let u be 5x, because then du would just be 5 dx. So now I can rewrite this as the integral of cosine of u, and then 5 dx is du. So what is the integral of the cosine of u? It's the sine of u plus c. So now I'm going to rewrite it as the sine of 5x, because u gets replaced with 5x plus c. So we've done all 4 of those. Now, if you're ever not sure, remember you can always find the derivative. So what if I took the derivative of sine of 5x plus c? Well, the derivative of sine is cosine of 5x, but using the chain rule, I would then take it times 5. And then plus c, the derivative of any constant, is 0. So this would be what I ended up with for my derivative, and it should match what I started with. And in fact, it does. So when you're looking, say, at other resources, in case you're looking in your textbook or looking at other videos, note that you won't always see the rewrite in terms of U. So when you're doing just straight up pattern recognition, you're making sure, for instance, that this fits the pattern, and then you can go straight to here. So you can skip a lot of the work, but I find that as students really just get started, it's best to do a rewrite in terms of U, integrate, and then replace whatever your function of U was back into the original equation. The last 4 examples we just did, I said were just straight up practice with no crazy tricks. So now let's talk about what some of the crazy tricks are. This one's not too crazy. This is when something almost fits the pattern. We can use multiplication or division to make the pattern work. So let's think about what we would do for this first question. Remember, I would say, well, this is some function that's being squared, so that's the composite function. So I'm going to think of U as x squared plus 1, and then du as 2x dx. So if I'm trying to rewrite this integral, this is u squared, but notice du is 2x dx, and that's not what I have. I have 1x dx. So if this doesn't work, we can make the pattern fit by saying, what if I take this times 2 here? Well, to be mathematically correct, if I take it times 2, I also have to take it times a half, because 2 times a half is 1. So what I'm doing is making the pattern fit, but without changing any of the values. So now this is 1/2 of the integral of u squared du. Again, how did I do that? I said, well, I need 2x dx on the inside, so let's take it times 2 here and divide it by 2 on the outside. So now I can integrate and say this is 1/2, and then u cubed over 3 plus c. So this is actually just u cubed over 6, so x squared plus 1 cubed over 6 plus c would be my final solution. Let's do the same thing for the second one. I have u as x squared plus 1, and du, of course, would be 2x dx. So it's very similar to the other question that we did. This doesn't quite fit the pattern because I need 2x dx. So, and I have 3x dx. So I need to divide by 3 here. But if I divide by 3 here, I need to multiply by 3 on the outside. And then I need to multiply by 2 here, but if I multiply by 2 there, I have to divide by 2 on the outside. So really what I'm doing is taking the inside times 2/3, so that I end up with just 2x dx, and that gives me the 3/2 on the outside. So 3/2 times the integral, this is u, so u to the 4th, and then 2x dx gives me du. So now I can integrate. Keep the 3/2 on the outside. This is u to the 5th over 5 plus c, and then we replace c, so we have 3, and then u to the 5th would be x squared plus 1 to the 5th divided by 10 plus c. So that's just making the pattern fit using multiplication. We're going to call this one forcing a pattern to fit because, as you'll note, this one actually has an extra x in it. So as I'm working through this, I would call u 2x minus 1 and du 2 dx. And notice that doesn't fit a pattern because 2, I have dx here, but I would need a 2 here and a 1/2 here, and I still have this extra x to deal with. So this is not something that you'll have to do very often, but again, it's one of those really nice tools to have in your tool belt. When I have something like this with an extra x, I'm going to look at the fact that u is equal to 2x minus 1. That means u plus 1 is equal to 2x, and then u plus 1 divided by 2 is equal to x. So when I rewrite this with respect to u, I'm going to write this as the integral And again, I do still need to include the 2 and the 1/2. So I have 1/2, and then 2 dx is the du. This is u to the 1/2, but then x is u plus 1 over 2 du. So this one got pretty ugly pretty fast. So I'm just going to do a little bit of cleanup before I continue. I'm going to go ahead and take this u and pull it to the outside. So I have 1/4 the integral, and then u to the 1/2 times u is u to the 3/2, and u to the 1/2 times 1 is u to the 1/2, and that's all with respect to u. So now I'm going to integrate. I get 1/4 still on the outside. U to the 3/2 would be u to the 5/2 divided by 5/2. So 2 u to the 5/2 over 5. And then plus u to the 1/2 would be u to the 3/2 divided by 3/2, or 2/3 u to the 3/2. 2/3, and then plus c, and then I would just do a little bit of cleanup. So this would turn into 2 and 4 would reduce. That would give me 1/10 u to the 5/2. This would give me, let's see, 2 over 12, so 1/6 u to the 3/2 plus c. And then, of course, I could replace those values with u. Now, you could do more cleanup here. So I could worry about what could I take out of 1/10 and 1/6. So I could take out a 1/2. I could worry about how many u's can I take out. But just for the sake of time and clarity, I'm just going to replace u with 2x minus 1. This is to the 5/2. And 1/6 2x minus 1 to the 3/2 plus c. And then keep in mind, yes, I could do a little bit more cleanup to make it a little bit of a more simplified answer. For our last question, we're actually going to find the equation whose derivative is the cosine of x over 2 and passes through the point 0,3. So just as I have on all of the other questions, I know that the derivative is the cosine of x squared, so that means I need to take the integral of it to find the original function. So cosine x over 2 dx. Now, do I have to worry about u-substitution? Yes, because this has a derivative. So u is actually x over 2, which means du is just 1/2 dx. So why do I need that? Because I need this pattern to fit. So I need 1/2 dx inside the integral, so I'm going to take a 2 on the outside. So 2 and 1/2 turns into 1, and that's why that works. So now I have that the original function is equal to 2, and then now I'm going to integrate cosine of u du. So 1/2 dx was the du, and then cosine of u. So if I integrate that, I end up with 2 and then sine of u plus c. And then, of course, I would just say that f of x, because that was technically f of u. And now if I replace u with x, this is 2 sine of x over 2 plus c. So that's kind of where we would end, except for now they want us to find the equation that passes through the point 0,3. So we're saying when x is 0 and y is 3. So I'm going to replace f of x with 3 and replace x with 0 and then plus c, and I'm now solving for c. So this is kind of the ending point, and then we start again using the point 0,3 here. So we get 2 times sine of 0, and sine of 0 is 0. So I have 3 is equal to 0 plus c, so 3 is equal to c. So what's my final solution? The equation whose derivative is cosine of x over 2. It's this function, except with c, c as 3. So f of x is equal to 2 sine x over 2 plus 3. Now again, could I check my work? Of course I could. Let's find the derivative of the function that we just found. So f prime of x would be the derivative of this. What's the derivative of 2 sine x over 2? Well, I would have 2, and then I have cosine x over 2, but then I would take the derivative of x over 2, which is 1/2, and then the derivative of 3 is 0, and then 2 and 1/2 turn into 1, so this just gives me cosine of x over 2, which, hey, is where we started. Up next, we're going to do the exact same thing for definite integrals, but we're going to call it change of variables because we're actually going to show two different ways on how to use those limits of integration.